Alright, I wrote down all of these things, and I'm going to go through them right now. I'm going to use my pointer. Look at that. This is like a little laser light. Okay, so in this section, it's going to be talking about graphs and characteristics of graphs and what the derivative means for the graphs, which you already know, and the second derivative, which you already know. You know all of this because you guys are geniuses, right? Right? Am I right? Yeah. Oh, see? Okay, very good. Mean value theorem. We've talked about this before. The mean value theorem says, well, first there are two conditions, and sometimes the questions are very, very specific about these conditions, so it's good to know these. If f is continuous on a closed interval, that means you include a and b, and if f is differentiable on that interval, so another thing that I like to think of is like if it's smooth, so smooth, meaning there are no cusps or corners or anything like that. So if it's continuous and smooth, then there exists some c value such that, so some c value in this interval such that the slope at that c value, that's what that means, is equal to the slope of the secant line between a and b. And there's a picture that goes along with it. So let's say it again, and then I'll go up to the blue part. So if there's a function, oh look, the green part, that's the function. If there's a function and it is continuous from a to b, I should say a to b, and it's continuous on this closed interval, meaning there are no holes, there are no jumps, there are no corners. Actually, continuous, you can still have a corner if it's continuous. So there are no discontinuities. But also it's smooth, so no corners, no cusps, meaning you can take the derivative, it's differentiable. Then there's at least one c value in the middle, such that when you get the derivative, like meaning the slope, that is going to be the same slope as the slope between the endpoints, which is the slope of the secant line. So there can be more than one, of course. If you had something like this, then of course there's more than one. But the mean value theorem guarantees that we have at least one. That's what this is saying. So this is the slope of the function at some c value inside a and b, inside that interval. And this is the slope of the secant line. That's the average rate of change between those two. So that's what that means. That's what the blue stuff says. This means if f is continuous on the closed interval and differentiable on the open interval, then there is at least one. That's very important because there could be more than one. At least one c value such that the slope of f at that c value is the same as the slope of the secant line between the endpoints of the interval. So that's what that means. Okay, we're going to move on. This is actually very, very intuitive, the next part, the extreme value theorem. It just means if you have some function, f, and it's continuous on some interval, then there has to be an absolute maximum and an absolute minimum. They could be the same thing. You could have something like this, say that's a flat line. This is for the extreme value theorem. Okay, then there's a max and then there's a min. They're all, every single point on that line, if this is a perfect horizontal line, would be a maximum and a minimum at the same time, because it's the max in the interval and the minimum in the interval for the y values. But the extreme value theorem guarantees that you'll have an absolute minimum and an absolute maximum. Could be something like this, where max is there, minimum is there. If it's continuous, then we're good. If it's not continuous, this is the important part of the extreme value theorem. If you had something like this, and there was a hole at the top, something like that, then we don't have an absolute maximum, because here we can like zoom in and zoom in and zoom in. I can't zoom in anymore, but we can like zoom in and get closer and closer and closer to this y value, but never touch it. So this doesn't satisfy the extreme value theorem because it's not continuous. And it has to have a closed interval. So if I had something like this, and I said, well, what if I have like an asymptote, like the x-axis is an asymptote? Well, if I never close this right side interval, then I don't have a minimum value, because I get, the farther I go out here, the closer and closer I get to y equals 0. So it has a limit, it has a bottom limit, but it doesn't have a lowest value, because I can get closer and closer to 0. If you pick 0.1, I can pick 0.01. If you pick 0.01, I can pick 0.001, and that could go on forever and ever and ever. So it has to be on some closed interval. That's the extreme value theorem. Hopefully that's intuitive, but those are the cases. So if it's continuous on some closed interval, continuous and closed interval, then it has to have an absolute max and an absolute minimum. That brings us to finding these extrema. There are two types of extrema. First, there's the absolute, which we just talked about. Absolute max, absolute min. That's the same thing as global maximum or global minimum. Those are the highest on some interval. You could actually have, let's draw some pictures. You could actually have a global maximum on an infinite interval. So like you could, from negative infinity to positive infinity, you could still have a maximum, global max or a global min. It would just have to be something like a parabola. That doesn't have an absolute minimum, but it does have an absolute maximum, and vice versa if it's flipped upside down. So absolute maximums or absolute minimums are on some interval, could be infinite or closed. You have a highest y value or a lowest y value. That's what global extrema are. And then if you want to find local extrema, that's when there's like, you can zoom in to a point. So if I have something like this would be a local extrema because I can zoom in on some interval, and then there's a highest point. There's, like, if I zoom in really, really close, it will be the biggest point in that interval. It'll be like, if you zoom in close enough, it'll be the absolute maximum or minimum in that interval. So like any of these would be local extrema. Just means you can zoom in and it will be the biggest. Yeah. To find the local extrema, you take the derivative, so take a derivative, and set it equal to 0. We're finding the critical points, so you set it equal to 0, solve for the values that make it 0, the derivative, because that's looking for where you have a 0 slope. Right here, that's a 0 slope. If you have a 0 slope, chances are that you could have a local maximum or a local minimum. To figure out whether you have that, you do a sign chart for the derivative. Remember, it's definitely for the derivative, because you want to see when the derivative goes from increasing, look, that's increasing, to decreasing. Sorry, not the derivative. You want to know when the function goes from increasing to decreasing. That is the same thing as saying you want to find out when the derivative goes from positive to negative. There's a very clear distinction there that I almost messed up. The function can be increasing or decreasing. The derivative is positive or negative. If you say the derivative is increasing, this is super, super important. So many people get this messed up. If you say the derivative is increasing, you're talking about the second derivative, because increasing implies the rate of change. So if you're saying the rate of change of the derivative, that's the second derivative. So be very, very careful when you're writing this out on like a free response. If you say increasing or decreasing, you probably should be talking about the original function, increasing or decreasing, which means you're thinking of the derivative. If you want to say the derivative is positive or negative, make sure that's what you're saying. Okay? So that's something that's super important. Hopefully you can make that distinction and remember that distinction. You use a sign chart, look for where f prime changes sign. That's f prime goes from positive to negative or negative to positive. That means the function changes from increasing to decreasing or decreasing to increasing. So you could have a what was a local extreme there. And then also to find global extrema on some closed interval, you find the local extrema, and then you have to check the endpoints, because you could have something like this, where you have some function and, okay, great, you find all of the local extrema, bam, 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 you test out their y values, and you find out that one is the highest y value. Great. And then from your local minimums, you find out that that one has the lowest y value. But if you don't check the endpoints, then you miss out on the actual global minimum. So this is the global min, this is the global max. So it could be at a relative or local extrema, or it could also be at the endpoints. So you do have to check the endpoints. That's what this part is saying. Then check the y values at the endpoints to see if you have an absolute minimum or max at those endpoints. Yeah, if you plug in, say you plug in these y values and they're smaller than the y value that you found with the local extrema, then at that local extrema, or extreme, at that local extreme you have a global max. So this video is too long. One more thing though, real quick. It's possible to have a maximum or a minimum when f prime is undefined. That's like when you have piecewise functions or absolute value functions. So, I mean, those are kind of easy to spot because you know specifically where that's undefined or where that doesn't work out, because you can see it in the definition of the function because it's piecewise. It's where it changes. But you can, so like it's important if you have a piecewise function to check the parts where the piecewise function switches from one function to another, because those places could also have a minimum or a maximum. You just have to check them. Okay, I'm ending this video. There's tons more, but I'm going to end it here.